Hi everyone, welcome to my channel. I'm glad you're watching. I would like to share with you my physics theory on the speed of light. First off, I want to tell you what the theory is all about, and then I would like to present you with a couple of thought experiments so you can fully understand how I got there and the implications that the theory has. Hopefully I can give you a good explanation of what I see with my mind's eye and make it simple enough for anyone to understand. So let's get started with the theory. The speed of light is not the speed limit of the universe. It is merely the horizon, just like our normal horizon. Anyone with a different velocity is not looking at the same photons, well, at least the effect of the same photons that you are. With this, I'm saying that the speed of light is not the one absolute truth. It's just the horizon, and that's all. And yeah, it's consistent because the horizon is consistent, but it's not consistent in the sense that the velocity itself is maximum velocity. We all know the Earth doesn't end at the horizon. This is by far the most difficult thing I've ever had to record. It makes me so nervous to talk about these things. So here's the first thought experiment. The first experiment is the journey of a photon. It's a ray of light coming from the sun onto an unfamiliar planet that doesn't have an atmosphere, but that does have water. When light, a photon, moves to this planet with only a lot of water on it, and it reaches the water, it actually bends like the rays of light do on Earth when they hit the water, and the light slows down. So if you look from an outside observer, close by this planet, or actually just swimming around on this planet, you'll not see this photon, but you'll see the sun and understand that the light that hits the water comes from that sun, and you actually see the light partially reflecting and partially hitting the water, bending and slowing down. Now, that light is traveling slower in water. It's kind of hard to see, but you could measure it if you have the right tools with you. But it is more interesting to look at this from the perspective of the photon. So the photon, you're a photon, and you're born at this sun, and you travel all the way, very fast though, to this planet, and you hit the water. You go into a different direction and you go a bit slower. Now this is the journey of the photon thus far, but the image is not complete. The experience for this photon is very, very different, and it's about two different aspects that I'm going to explain with other thought experiments. So we're moving on to thought experiment number 2. Maybe you've heard of the thought experiment of sending a rocket out of space and try it to go so fast that it reaches the speed of light. Now the theory goes that you can never reach the speed of light because E is mc squared, and thus you'll need infinite amount of fuel to take with you in order to get to light speed. And since this is impossible to do, you can never reach the speed of light. When I heard about the theory, I realized that I could look at it in a very different way. What if you do not send out one giant spaceship with a limited amount of fuel, but you just have a normal spaceship, a normal amount of fuel, and you go to a planet that has a velocity lower than yours, otherwise you can never reach it, and you play tag. You go to that planet, you tag, and another rocket ship takes off, and it will have the same velocity as you did, but it had a faster starting point if you compare it to Earth, where you left in the first place. So you might say that this spaceship has speed X and this spaceship has speed Y, and you can continue this pattern of tagging spaceships. It's the same as, if you have a runner and they tag someone that's already on a running machine and they go running. It's different, right? And you can do this infinitely. You can say, well, there is this thing called space-time, and this means that space bends and time distorts, and so your theory doesn't work because the sum of all the velocities is not going to add up. Now, this is true, but it's also not true. It is both true and untrue at the same time. So I drew the little spaceships and planets over here, and as you can see, on one hand, the velocity accumulates on the adds, and in the end, these numbers will not add up. But regarding to this planet, the speed of this little spaceship is 1,000, and relative to this planet, this is 1,000. So both are true at the same time, even though there's going to be a mismatch between the high velocities, especially with the bigger distances. The more spaceships you have, the bigger the difference is going to become, and that's because of the bending of space-time. I drew a picture that makes it even easier to understand. Now, a velocity is a vector, and I'm talking about speed here, since the objects that are moving are all moving in the same direction. My point is the point of relative velocity. If you're on Earth and you take a spaceship and you then go with 1,000 meters a second, and both the person on Earth and you will, in the spaceship, will understand and see that the speed that you're going with is 1,000 meters a second. Now, maybe you see this asteroid flying in the same direction as you are with 1,000 meters a second. However, the person on Earth is saying this same asteroid is going with less than 2,000 meters a second, but both are true at the same time. There's going to be a difference between the experiences that they all have with their neighbors and the picture as a whole from the first one in the chain. Now imagine there is actually a velocity horizon, and these spaceships here, they're actually going so fast that this one is already at the speed of light. And the vision from this one is that here's the velocity horizon, and it cannot see what happens beyond the horizon. Now it is true that big heavy molecules go into wave mode at a much lower velocity than photon particles do. But if we look at the farthest as possible velocity in which we can still observe and interact, then the speed of light is the final horizon, so to say. Now we can add in some more spaceships that are even going faster.
Curve explains why the velocities do not add up, even though the measured speed of the direct neighbors is correct.
So I drew some more spaceships, as you can see, and you can not only see that they go beyond the velocity horizon, they actually go all the way around. And when we look back at our precious planet Little Earth in the first rocket, then we can see that actually something can go away from us so fast that it is the same as something getting closer, moving toward us really slow. So going extremely fast is the same as something moving towards you very slow. And remember that this is in all directions, because this is just a flat piece of paper. But you can have something going this way or this way, and you can imagine it as a real globe. And anything that moves away from you very fast is actually moving towards you very slow. So the faster it goes, when it's reached a certain threshold, it's actually not something anymore that's going away from you, but it's actually going towards you, first at very high speeds. And you can look at it the other way around as well. So something that looks like it's slowly moving away from you is actually the same as something moving towards you really fast. It's kind of cool, right? Imagine when you walk to the mirror that it's actually an object moving away from you very fast. And it brings me also to this concept of having zero velocity. Maybe you think like, I don't have zero velocity because I'm on Earth spinning very fast, I'm in my car driving, but this is not true because you're always the observer. I've never been observing anything but my own experience, and I've always been the one standing still, and everything around me is moving. The horizon is as fast as it is because of the fact that I'm always standing still. And everything around is moving. This is the same principle as you can see in computer games very easily. Like you had the old Mario, and he used to walk from left to right across the screen and save the princess. But actually, Mario was not going anywhere. He was standing still. He was just moving his legs like that, and it's the backdrop moving. Now this is the same thing that is happening in your entire life. You've always been the one that's standing still, and everything around you has always been moving. And this also makes it easier to understand that you can never go out of the universe, and that you'll always be right in the middle of it no matter where you go. It also makes it easier to understand that no matter how fast something goes, it's either moving away from you or moving towards you, and it's not a different thing. It's not something else. It brings me, however, to another question, and it might be something that you've been thinking about as well. If the speed of light is not maximum speed, and if something that is going really fast is actually going really slow but in the other direction, then what is the maximum speed of the universe? Now I have to expand a little bit on the thought experiment we just did. If we look at the paper and we start off from where we are, we start with the zero velocity. And something that is zero velocity is just mass only. So this is our starting point. And we're massive. Can't deny it.
This is funny because actually you're the energy within mass, and every bit of energy contains the nature of mass, just like your consciousness is inside of mass.
And yeah, we contain energy. It's always coming and going. It's important to realize what mass is, what this starting point is. If you have a rock, it's pure mass. Then if that's all there is, nothing is ever going to change because there is no energy. And since there's nothing to change, time is going infinitely slow. So time is not existent, it's zero, because there's only mass and no energy. But there's more to this, because if you close the circle, then at the bottom, so we have energy. So here in the middle, we have energy. And energy without mass can never interact with anything because there is no mass. It is going so fast because there's never any resistance. It's going infinitely fast. Thus, when there's only energy, there also is zero time. But there's zero time in the sense that it's the exact opposite of the situation with energy. There's also zero time. There is zero time in the same way as is the case with mass, but it's the exact opposite, because if you only have mass, time is so slow, it's infinitely slow. And if there were to be only energy, time is so fast that it's infinitely fast. I easily explain this with the velocity horizon model. If there's energy and it's beyond your velocity horizon, it is impossible for that energy to interact with you. And since there's no interaction, there's no resistance, and its velocity is therefore unlimited. I want to give you another picture, another point of view to understand how distance changes with the effect that mass and energy have on time. So here is our little rock, and if we go over here, you'll see the velocity horizon. So imagine you're standing there and you're looking at the velocity horizon just like you normally do. Now, just as with our normal horizon, the distance that you perceive there is to be is going to be shorter near the horizon. What we consider to be a meter here is a very short piece over here, and when it crosses the horizon, it doesn't even exist. It's zero. But this is only from our perspective. So this is a relative fact as well, that everything beyond your velocity horizon is obviously this last little line here, that last distance, that is exactly the speed of light. And everything beyond that is what we cannot interact with. What is really mind-blowing about this is if we go back to the little rockets, you'll know that this one will be going faster than this one, and this one will be going faster than this one, and so forth. But still, when we curve it all the way around, you'll see that these are all beyond our velocity horizon.
So to us, they are all going infinitely fast.
What to us seems infinite are, this one is going infinitely fast for us, and this one too, because we cannot interact with them. These are beyond our velocity horizon. They do see that they both have different velocities, and they interact with other things because they have their own velocity horizon. And for them over here, this is not energy, it's not energy, it's mass. And to them, we are energy, and we're actually outside of their interaction field, and they don't see the difference between our spaceship and the next one, because to them they're out of the interaction field and going infinitely fast. Now I'm ready to finally take you back to the first thought experiment. When we look at the first thought experiment, we see something quite different from the perspective of the photon. We know now that this photon being born
Can have a velocity at the speed of light or even higher.
if it is beyond the velocity horizon, it will just pass through. But if it's a photon that is on the velocity horizon, it's one of the lucky ones that they are able to interact, being a massive object, with something that they previously did not see, but they're somehow interacting with. So the experience of the photon is exactly the same as the experience of the planet. This might sound kind of weird, but to the photon, it is mass, and it has a different velocity horizon, so it's seeing a lot of different things, and it finally hits something that it doesn't even see. And when it hits that something, it sees it as a photon. And we'll never know the other experience, except for the fact that everything around us is constantly going from a particle to a wave and crossing horizons. This is the fundamental truth of what we're living in, and we can never ever do anything to not be we can never do anything to gain velocity and look farther on this horizon. This is where you're at. You have zero velocity, and there's your horizon, which is the speed of light, and everything that is beyond it happens instantaneously. But if it's going, and you know, it can be this fast or even a little faster, and it doesn't matter, you don't see the difference because it's instantaneous. But if something is going even a lot faster than that, then it's actually something coming at you from the opposite direction that you thought it would be going. Because we're just also in this way on a globe. So going forward, someone going forward, they are also coming towards you. Something going really, really fast. It comes at you very slow. And everything that's in between, really fast and really slow, has infinite velocity with regards to your experience. But actually, that's the exact opposite of the one observing from the other side, because they think that you and your little car and your little planet and your little bicycle are all going at infinite velocity, if they happen to be beyond your velocity horizon. Thank you for watching. I hope I could explain it in a way that is understandable and relatable, imaginable. Let me know what you think about it. Please like this video, share your thoughts with me, and maybe I'll see you later. Have a nice day. Goodbye. Thank you for watching.
I could not have made this video without the wonderful composers like Christopher Tin. I used music from Off-World, SimCity, and also from Corsi Final. I used images from NASA, and obviously some screen material from the computer games Super Mario Bros. 1, 3, and Res.